it's really hard to find the cause of the issue that doesn't exist. Not to mention, it's a huge waste of time. Hello, friends. Welcome back to the bench. Today, we're going to take a look at this PSU, the bench power supply. Don't you hate it when your repair equipment breaks and you have to repair your repair equipment? It happens. And luckily, I have multiple of these. I use this awesome Australian power supply, bench power supply, and I have one more of these. It's a very nice, cheap device. It gets the job done. It's maybe not the best to actually see what your current limiter is. You just have to drop the voltage, make a short on the output, and adjust your current potentiometer to set it to whatever current you want, and then adjust the voltage, and then you know what your current limit is. So not the best user experience, but it gets the job done. It actually can deliver, I think, 300 watts. I'm not sure. I think it was around 10 amps at 30 volts. If not, it's 5 amps at 30 volts. Maybe it's 5 amps, so 150 watts. So it's pretty decent power. The PSU is actually not bad. As you can see, I already disassembled it, or at least took the cover off to diagnose what's wrong with it. And actually, how it manifests is pretty curious, because when you turn it on, it flashes CC, or not flashes it. The CC diode goes, or LED lights up, and we got 0 volts on the output, 0 amps, right? And the CC means that there is well, that would suggest that there is a short on the output, right? But there is no short, and actually that's something we can check without even disassembly. Just put the probes over here, and check for short. There is no short, so our problem is somewhere else. And actually, I already know where the problem is on this one, and it's no different than any other. Not any other, but the most the most faults on PSUs. So we'll fix it. But let's take a look how it's built, and it's actually pretty curious, because the build is very basic, but the components actually are not too bad. The majority, let's take a look here. The majority of capacitors here are SMD caps. All these guys. We do have main. So this is our main output, and this resistor array, that's on the output, the main core on the output, the diode. The diode has a thermal feedback through this wire to this one or this one, that shuts off this control chip. This is our control chip. This is what actually produces our main output, and the transformer that is used to isolate the control circuit from the 2 main transistors that drive this transformer, goes through the coil, diode, resistors, and we have output capacitors, more coils. Here we have a passive PFC, bridge rectifier, PFC, VFE capacitors to supply 300 volts, or depending how you configure this this coil over here for 120 or 240. And here we have a standby transformer, the standby control chip, which is basically like a smart transistor, and not much to it, and that produces our standby. Our standby is fine because this lights up, and we do have a control over it, but there's just no output. As far as the PSU is concerned, there's either a short on the output, or something else is wrong. Basically, this chip shuts down. And the shutdown pin is pulled to the reference voltage, which means it will shut down. So it detects a fault. Now let's see if we can just hook it up and whether we can reproduce it right now. All right, the voltage went up, and now constant current, the CC, or as it's labeled here, switching mode. It's basically CC. It detected that the current flow is too high, and lights up this LED, which causes um, our control chip to shut down. And that's pretty much, that's how however we control this, right? No reaction. And we can hear the sound. I'm not sure how well you can hear it through the microphone, but it's making this noise of relatively low frequency, and that's what it behaves like. Now, what is the problem with it? Let's let it discharge. Yeah, those capacitors can hold a lot of charge. There we go. So now it should be discharged, or the majority of it should be discharged, but we're not going to be doing measurements just yet because I want to make sure that every cap is discharged. Now, our control circuit. So our standby, we know everything is fine with standby because we have the power for our displays. So our standby is fine. And I wouldn't expect anything to break with the standby, as it's controlled by TNY274. A very simple circuit. In this typical application, this is our chip, our control chip. As you can see, it only has a drain and source. So that's our transistor that controls the main transformer. And we have pretty much the power from the bootstrap circuit, and the feedback, which in this case is just a Zener diode, which is 11 volts, two resistors, or the voltage divider, and that in turn turns on the transistor, our optocoupler, which in turn pulls this pin low. If it pulls it low, the PWM goes down. If it goes high, PWM goes high. So that regulates the voltage on the output. So this is a typical application for 12 volts, 1 amp a power supply. Right, that's our standby voltage. But nothing wrong with that. So this is just for informational purposes. The heart of the device, what actually produces our output voltage, is SG3525A. And this is a circuit, or this is IC that I actually have some experience using, as this used to be like really popular power supply, heart of the power supply. I've built few power supplies myself on this circuit, and like kind of atypical, call it atypical power supplies, when the voltage requirement was like really ridiculously high, 3 kilovolts, and the output was supposed to be 300 volts, right, or roughly 300 volts. So I built it on this chip, and actually, because that was quite a few years ago, decades ago actually, and back then, well, the internet wasn't available as it is now in Poland. So primary source of information were the magazines, the electronic magazines, and that's where I used to get most of my circuits that I would reproduce to for my applications. And one of them was the power supply, right, built on this chip. So it seems to have been very popular back in the day. I'm not sure about now, but it's definitely cheap and it gets the job done. It has two transistors built of actually the array, the full bridge, H bridge, built in where we have output A and B. Right, these go to the big transistors that control the transformer. In our case, these two, and that's our main transformer. That's our control transformer. Just to insulate the floating ground from the ground, from the circuit ground. And as you can see, so this is the lab test fixture, right? This isn't typical application, but if you Google SG3525 typical applications, you're gonna get tons of circuits, and one of them will probably match this circuit exactly, because there's nothing much to it. But the idea is very simple. We have these two pins 1 and 2, which are our inverting and non-inverting inputs of the comparator or operational amplifier, however you want to call it in this case, which in turn through our adjustment potentiometer controls the PWM of the output. Right, so there's no feedback circuit, or at least not here. Here in our application, we have a feedback circuit because we want to control the voltage at set point that we control with the potentiometer. That's why we don't have the current display, what the current is set to. It's just a limit. It goes to the certain flow and won't get any further. Then the voltage is going to start dropping because the current is too high. So what do we have here? We have a soft start, right? Typical on soft start, or as I used to use it, is exactly as here. You just connect a capacitor, and that basically well, the name is kind of self-explanatory. It's soft start, right? It's not going to start with the full duty cycle that it's set to. It'll start very slowly. You can use soft start also as a shutdown, but you have dedicated shutdown a pin number 10, which you connect to the reference voltage, which shuts down the PWM, right? And as you can see on the diagram over here, or the schematic, those two are connected. So you could just as well, because if you supply a reference voltage to the shutdown pin, it will in turn pull the soft start low, right? So basically the shutdown is just the implementation of the soft start, you could say, or the wrapper around soft start. So you can you don't need to use shutdown, you can control it with soft start. You can achieve the same outcome. And that's pretty much it as far as this circuit. As far as the sync and clock, I'm not sure. I've never used these. I'm not sure what they would be for, but I guess some kind of external oscillator. But it does have built-in oscillator, so we don't need that. And I don't see any crystals over here, so looks like we're not using external oscillator, which is fine, because that's why this one has one built in. And that's pretty much it. Just one potentiometer, which controls the pulse width modulation. and now we can replace it. And this is actually, I'm not sure how it's done over here. I didn't really get into it too deep as far as reverse engineering, although the board is relatively simple. um, it's just two sides, there's no layers inside, so it wouldn't be too hard to draw a schematic for this one. But I'm very inefficient at reverse engineering and drawing schematics from the devices, so I didn't do it. Plus, I know what the problem is without that. I just wanted to know how it is built. And actually, that was pretty cool finding out that it's built on the IC that I'm actually familiar with. So that's pretty cool. Now, probably we are discharged, but let's grab a um, resistor. And first, let's make sure our big caps that hold high voltage are discharged. Um, okay, that's definitely discharged now. And I want to discharge the outputs over here. Uh, here and here. So this is low voltage side. So I don't need to worry about anything here. Just to make sure. And now why do I do it? Because I want to measure ESR, and I don't want any of these caps to have any charge on it, because that might mess up my measurements. First, let's make sure we are reset. Negative 1 so let's reset it. It's actually pretty close. Okay, and the ESR on our output is 50/40. Yeah, very good ESR on the output, which is great. Now let's see our SMD caps. So we have plenty of them here, and our measurements are, oh come on, okay, I have open line here. 170, not too bad, but not good. This one, 180, not good. Not terribly awful, but not good either. Huh, 1.23 ohms. That's like extremely huge. 122. And I also measured few others. But this one is that gives me 1 ohm, and this one coincidentally is here on, well, this one supplies the, what do you call it, the fan, or at least it appears to be on the output of the fan. I'm not sure because it's difficult to see, but I think it's on the output of the fan. So that's not too bad, but it should be, so here we should have a stable 12 volts. So I think our standby voltage, our standby transformer produces two voltages on 12 volts for the, unless this one's 5 volts, because it could be model 12 volts. So yeah, so this probably produces 5 volts for our logic and 12 volts for the fan. So it's not horrible that this cap has very high ESR. Probably not. Well, definitely not, because this standby voltage is controlled by this guy, which is like horribly sorry, which is horribly simple, extremely simple. So even if a high ESR on the output will likely not cause it to behave as it is behaving. But high ESR in these gaps, this one and these over here, most definitely will cause this. So all we have to do is just recap it. And actually, as I said many times, in most PSUs, even if they don't work and you don't detect any shorts, because obviously first you check these two transistors for shorts, you check this chip for shorts, you check if you have standby voltage, you check whether the control the chip is not shorted. This one wouldn't go short unless you really mess up the implementation of it or the circuitry of it. It shouldn't break, but it also happens. And once you confirmed all that, then just recap it and it should work. That's like 99% of PSUs. You just need to recap them. And for these frequencies, as why do these caps matter so much? Um, for PSU to work, it needs to constantly monitor the output. So it starts producing the control signal for the transistors. So it starts pushing energy into the transformer. One of the transformer windings is dedicated for actually powering this chip. So the first cycle is bootstrapping power for our for the control chip. Then the control chip takes over, starts producing the signal, starts oscillating the transistors, and starts measuring what voltage is being produced. How does it measure it? Well, the main consideration is that when the chip produces, let's say, a series of pulses to the transformer, then it measures, and it's doing it constantly. So perhaps it produces one cycle, so one pulse, then it checks the voltage. Another pulse checks the voltage. Pulse checks the voltage, and then based on that voltage, it will adjust the duty cycle. But if you don't have enough capacitance on the output, or your capacitors have high ESR and they themselves start consuming that current because the resistance is high, then the reading is wrong. So we made one pulse and we checked the voltage. The voltage is too low. So our PWM goes up. But by the time our PWM went up and we do another measurement, now the voltage is too high because the cap charged, and now the voltage is high. So we reduce the PWM, but the voltage is still high because the cap is still charged. So we shut down because we can't control the output. The output is abnormal. The same when we produce 10 cycles and the caps are still charging or don't want to charge, or basically the voltage is too low, and our duty cycle goes to when the voltage should be at a certain point and it's lower, we shut down because the output is abnormal. That's why the caps on the output of an PSU need to be in pristine condition and need to be low ESR for the device to work. And as far as the frequency on these, it's above 20 kilohertz, otherwise you would hear it. And you do hear it when PWM is really low, and some of them control also with frequency, some stay on a fixed frequency and just control the duty cycle. But when the duty cycle is low, you can kind of hear you can hear the harmonics. It's not because the frequency will be somewhere around 40, 50 kilohertz, so way above the threshold where you can't hear it anymore. The human ear cannot hear it anymore. The dogs perhaps can, but not us. But there's also harmonics, so we hear those lower frequencies of harmonics, which to us still um, sounds like a pretty high frequency, but it's indeed much lower than the frequency that the chip uses to control the transformer. So that's why capacitors are so important in PSUs, and that's why recapping in most cases will resolve all the issues with your PSU, as long as there are no shorts, because that's the other typical cause of PSUs, but of PSUs going down, going dead, and that usually is a result of poor design, or just kind of pushing it too hard. Uh, the Because transistors should be picked for the application to just basically not work more than 70%. I would say that would be the highest, 70% of its capabilities. So if it's designed for 10 amps, you shouldn't go above 7 amps, right? If, on the other hand, it's designed for 10 amps and you're pushing full 10 amps, if it's designed for 24 volts and you run it on 25 volts, that's usually when you're going to see burned transistors, it, or exploded transistors, or just basically shorted side. The other consideration would be the feedback circuit. The feedback circuit just allows too much current to be drawn, and so that's also the design failure or design issue. And in some cases, when the capacitors on the output um, go bad, lose capacitance, or ESR goes way too high, that's when the chip is trying to compensate and still produce enough voltage. Because as long as you don't have too much load on it, even with bad caps, it will work. But as soon as you put a high load on it, on the output, then the control chip is going to try to do its best to maintain the steady voltage on the output. And if the capacitance is low, then the PWM will likely go way too high, and that could also cause the damage. But that would still be considered a design issue, a design flaw, because it shouldn't. It should detect that the output is abnormal, like this one does, and just never turn on, never allow the current to flow. So this actually is a very well designed PSU. So in this case, it's basically not working because of the caps, and that is expected behavior. It's not going to damage itself, right? Alrighty, so we can probably conclude that these caps are not bad. However, measuring in circuit is not very reliable, and that's why I'm not even measuring their capacitance, because these are 2200 plus 15, no, plus 1000 plus this one's probably 2200. Sorry, yeah, I see, yeah, 2200. So our combined capacitance of the output exceeds the limitation of my meter. So I am gonna get open line on this one. So don't get fooled by that when you're checking the caps and it's showing you OL on the meter. Doesn't mean that the caps are bad. It might be too many of them in parallel, and the capacitance is just too high for your meter. and you know the my fluke goes only to about 1,000, and not not necessarily. My little one goes to about 4,000. Uh, or maybe a little more than 4,000. It doesn't say actually on the specs of this one. It's a cheap Chinese meter, but it's actually excellent. I gotta do a review of this one because it's like really I've had it for about a year now. It's excellent. It's one of my best meters, along with, so these three are my main measuring devices, and this was like ridiculously cheap, uh, straight from China. And alrighty, so I don't have these kind of capacitors, right? But I'll replace it with regular electrolytic capacitors. Um, I'll show you how to do it. Nothing, not much to it, actually. But the reason I'm doing it that way, this one's mine, and it did have issues, especially when working with laptops. Laptops will require a lot of current, and often laptops will require like a massive current in one peak, which causes this one to shut down. And I've misdiagnosed at least two laptops for power failures because of this power supply, because they would shut down when there's too much current being drawn. Not when they're on the battery, but when they're on the power supply only, and the computer shuts down. So okay, let's recap the board. Let's maybe replace the MOSFETs, and you know we fall into this deep black hole of diagnosing the issue that doesn't exist, and it's really hard to find the cause of the issue that doesn't exist. Not to mention, it's a huge waste of time. So it's imperative that you check your measurement devices, your lab equipment, before you draw any conclusions on what is broken with the laptop. So I fell into that hole twice already. So and now I will address it, since it broke. Because before I just never had time for doing that, because there's always something more important to do. But I wanted to replace the capacitors on this one with higher capacitance, so it can withstand those peaks that laptops require. All right, let's get to it. Alrighty, the board is out. The measurements, the capacitance measurements on the capacitors are way off, and I'm gonna replace them with these. These, come on. Okay, let's do that. Let's go. These are the cups you would find on a GPU or motherboard. 16 volts, 270, and I'm replacing all 220s. And oh, and we're gonna do it quick and easy like this because they're dry, so I don't care. Alrighty, now the question is, will it work? And here's a curious thing. So this one, these three caps are from the main output. These three over here, 1, 2, 3. They're respectively 2200, two of these at 25 volts and 1000 at 50 volts. I'm not sure why this one is rated for 50, but these, the PSU is 30 volts. So 35 volt cap is a little low. On regular PSUs, the computer PSUs, 16 volt rating goes to 5 volts and 25 volt rating goes to 12 volts. So for 30 volts, I would expect a 50 volt cap, not 35 volt. That's why these are being replaced. I don't have the caps that actually would fit because I don't have 35 or 50. So I put in 25 volt caps, the ones that I use for computer PSUs. And so we need to be careful about what voltage we produce with it. But just to check that this will resolve the problem. So this one measured 300 microfarads instead of 1000. So low reading means most likely it's dry. We can open it and actually check. This one was a little low, within 10% lower. This one was a little high, within 10% higher. So normally that's good. Actually, this one was almost 20% higher. So, no, was it 24? No, maybe around 10, 15% higher. So if it's 10% off, that usually means that's probably not your main problem in the device. But if it's off by 10%, then it's still worth replacing. And actually, on devices like these, replacing caps once a year is a good bet, just to keep the device working properly. Now let's see what's gonna happen if I connect it. Hopefully I connected all the cables properly, but I did it in such a way that I can definitely find which one's which. We're connecting through the light bulb, so even if we catch a short here, it shouldn't be a problem. And it's still behaving the same way. Take a look at that. Okay, so none of these caps were the problem. That's weird. That is curious. But when we turned it on, the fan span up, even though I haven't replaced the cap on the fan. And as you can see, I haven't replaced all the caps. Let's give it another try. Not that it matters. Yeah. Curiously, it goes to 12 volts. And again, the fan started spinning. Okay, looks like we need to replace more caps on it. That is, I was almost sure that replacing just these, especially this one, will get the job done. But indeed, the rest of these, they are also dry. All right, well, let's disassemble it and try this again. Alrighty, so I was wrong. No way around it. Unfortunately, after replacing every single capacitor on this board, I concluded that it's not capacitors. Every single one. Because I was so sure it would be capacitors. And actually, there are still some on this board, but I really doubt they would cause this issue. So, a very time-consuming and very ineffective method of confirming that it's not the caps. So let's do what we should have started with. I shouldn't have jumped to the cap conclusion, but the reason I did is because when I was measuring the first time, before I even started recording, it, it started working, right? So that's kind of typical for damages resulting or malfunctions resulting from capacitors. They are intermittent. Sometimes they work, sometimes they don't, depending on the, I don't know, maybe temperature, maybe pressure, maybe humidity. Who knows? But it happens. It happens actually a lot. So that's why I concluded it would be a recapping job. It doesn't seem to be a recapping job because I'll show you very quickly. So this is like a typical application of this chip, right? Very simple. How does it adjust or how does it work? So on CT and on discharge, we should see a frequency of about 50 kilohertz. That frequency is actually controlled by the RT timing resistor. Our feedback circuit, our feedback loop, is connected, well, basically to pin 1, which is inverting input. Our pin 2 is non-inverting. And non-inverting is connected to the reference voltage in this case. In our case, it's not, but that doesn't matter. In this case, it's connected to 5 volts. We have steady 5 volts on the reference pin. And if the voltage drops below the non-inverting input, then the duty cycle goes up. If the pin 1 goes higher than pin 2, so inverting input goes higher than non-inverting, then the duty cycle goes down until it basically shuts down. So if the voltage on pin 1 is lower than the voltage on pin 2, that's when we're producing voltage by controlling these transistors, right? So very simple. So now let's check the device. So first the voltage. So on pin 16, we have steady 508, 509. It should be 5.1, but obviously my meter is not going to be that accurate. So we know it produces reference voltage. Now on pin 5, 2, 4, 5 is I think this one. We have 2 volts. 2 volts means that there is frequency if you don't have an oscilloscope. I do, so let's check it. Okay, that should work. And now, without making any shorts, preferably. So this is our discharge over here, right? We have, well, it's reading frequency all over because it's very small peak. And this is when my microphone decided to die. And unfortunately, it doesn't give you any signal that the battery died on it. So the rest of the video I recorded without the sound. So let's make a quick version of it. This is actually very simple. So the last measurement you've seen was on the discharge resistor, a very tiny signal. The next one, the nice square wave, we were getting on the CT. So frequency is working, and then we checked the shutdown. Shutdown needs to be pulled to ground for it to work, and indeed it is. Then the voltage on inverting input needs to be lower than non-inverting input. If it's lower, the duty cycle goes up. If it's higher, duty cycle goes down. That's why it's connected through the resistor divider directly from the output. That's our voltage. All right. So once this goes to whatever voltage it should go, maybe 12 volts, the voltage over here will be 5.1, right? Because that's our voltage um, on our non-inverting input. So if we confirm that the voltage here is indeed lower, but we still don't have a signal on the transistors, we can conclude that our SG is malfunctioning. And this is exactly what I'm seeing in the device. So this was a huge waste of time, or at least recapping was a huge waste of time. Definitely don't do it my way. Don't jump to conclusion that it's going to be on capacitors. I did and wasted huge amount of time, like literally wasted. This was not necessary. I should have just checked for this and maybe, yeah, maybe just kind of fool it to make it turn on. But in this case, I don't have to because this voltage is low, or at least lower than pin 2. So it should be turning on. It's not turning on. And that's pretty much it. So I conclude that the SG chip is malfunctioning. As far as the whether I'm gonna repair it or not, in this case, I will not repair it. And the reason is very simple. The chip is buried over here in between all those caps. And there's tiny components all around it really tightly. So wicking is going to be very difficult because there's no room to maneuver. Heating it with hot air, it's also going to be very difficult. I would probably have to remove the caps and then treat everything around here because we have plastic, we have small components. I just put put Captain tape on everything. So that's a lot of work to get the device that is worth literally $30. Too much work, right? Even recapping that was a bit too much work for as far as the value of this device goes, right? But mainly we did it for learning purposes. And I hope at least now we're gonna be familiar with the SG power supplies. These are not that popular, or at least not in the power supplies that I usually work with, which is ATX PSUs. And but this one is well, this one is very simple. It's roughly what we see on the circuit over here. It's a little bit more, obviously, a little bit more complex, but it's roughly what it does, right? Or this is roughly how every power supply built on this IC is going to work. On ATX PSUs, the computer PSUs, we have usually active PFC. We have whole bunch of difficult feedback, whole bunch of electronics that monitor the PSU and the voltages, and appropriately so, because you connect very expensive devices to that PSU. So, it will do everything in its power not to produce too high voltage, not to keep pumping voltage when there are shorts, that kind of stuff. So obviously, this is the PSUs will be definitely more difficult to repair. This one I was really hoping I would repair it, and I was actually sure that I would repair it, and so that actually caused me some depression for a day. And then I figured I'll just do the measurements, and I actually have a few more tricks up my sleeves if I really wanted to fix it. But I have much more interesting things to work on. So this one is going to the parts section, and I'm not saying this is no fix just yet, because it all depends on how much time I'm gonna have in the future. So I might come back to it relatively soon. We'll see. But hopefully you've seen something that was interesting, or at least a little bit entertaining. I thank you very much for watching, and I'll see you guys in the next one.